Hello, everyone. My name is Randall, and I'm a cloud solution architect here at Oracle OCI. Today, I'm joined by my friend and colleague Sudha, the Senior Director of Software Development and the OCI Services team. Today, we are presenting a session on building real-time event processing apps for analytics. And it's true, you can have both real-time reporting and deep analytics sharing the same data ingestion and processing platform. So let's get started. We're presenting a real-world design, but more importantly, we're also presenting the design principles used to define this architecture. We will discuss the design principles and then how they apply to this or any related application you may be interested in. We will also show practical code techniques and options to implement these principles. And finally, we'll post some links and code samples for your reference. When you hear event-driven, IoT may come to mind, but there are many other types. In fact, really it's more of a modern approach rather than just a workload classification. It's a message push model with distributed and most often non-deterministic event generation. It's certainly related to other similar workloads and shares the same underlying infrastructure components. However, mobile apps are typically interactive and bidirectional, while general messaging apps may be a data exchange or use a pub-sub model. Events are dynamic state changes or measurements. How the data will be used is, of course, also very important. Event data can be used in real-time or near real-time reporting and alerting, or for supporting complex analytics. Most often, the data is used for both purposes, even if that was not the original intent. There are big advantages to your business adopting this approach. It's very responsive and proactive to any changes and alerts in your environment. It can also reduce time to leverage valuable data. It's more of a real-time ingestion and processing at analytics rather than a batch-driven model. There's also big advantages, technically speaking, for development and operations teams. When using decoupled and redundant components, the stack is very performant, resilient, and flexible. It's also very scalable and can accommodate load spikes without over-provisioning and overpaying. Being serverless, it's also typically much easier to manage in the long run. So let's take a look at some features. In this high-level diagram, it's important to look at some of these core components. We'll build upon this in complexity and come closer to a production stack soon. In this particular diagram, you can see in the upper left corner that the event generation, the real-time data generation, is external to the stack. That is not always the case. Sometimes you are trapping and catching and processing events within your own environment. In this particular case, to match our real-world example, these events are generated external, and the stack is exposing a API endpoint to receive this information and process it. It's very important to have a very scalable buffer, in this case, implemented in a stream system, to be able to accommodate load spikes. The dynamic processing is implemented in a stateless fashion, either in functions or containers. And as you can see on the right-hand side, the same data ingestion and often the same data sets, same data storage system can support both your real-time analytics and reporting and alerting, and also your more complex analytics as well. So let's take a look at the real-world example we're referring to. This is a real-time facial recognition system, and it's actually becoming more common than you may know. I don't intend to get into the debate of Big Brother, but it's often used for augmenting security controls, primary security controls in an office complex or a public-private venue. So in addition to perhaps your badge, it's more of a passive security control, can identify where known authorized personnel have access to certain areas, or if an unrecognized or potential security incident is unfolding. Also used for reporting or analyzing any events that may have occurred in the past. This type of application aligns very well with the flexible cloud capacity, being able to scale up and down despite having a potentially unpredictable load rate. So here's that same configuration, adding a little more detail, getting close to a real production environment. As you can see, these the images are captured by security cameras and fed into the system. So we have this up and running. We're going to take a look at how this was built and why it was built this way. But first, let me show you how we're going to visualize this data. Here's a simple dashboard made in Grafana. I'm sure no one's going to be impressed with the simple dashboard, but it will be populated with data. We're going to start that up in a moment. Takes a few seconds for the client processes to start up. No, I did not hack into Oracle's security video systems. I'm using a public data set of faces. I have assigned some to be actual employees and some to be visitors and so forth. So feeding the system with that data. And from there, you can see we have an API gateway. Now, API gateways are important to provide a very secure and long-lived fixed entry point. Also, the API gateway manages routing and other security controls as well to provide, again, a fixed entry point that clients may be configured to be using. This architecture also uses functions, serverless functions for authentication, routing to streams, core processing, and so forth. I like to call that the heavy lifting. We'll certainly talk a lot about that later. Streams are very scalable, low latency message platforms. It's based on Kafka compatible components. They scale very well and are used to buffer and process messages in extremely low latency fashion. And again, you can notice how the same data flow, the same data repository and processing network can be used to support both real-time dashboards and analytics. Let's take a look and see if we have data flowing in our dashboard. So it has started flowing, and this is an example of a real-time or near real-time dashboard. And on the upper left, you'll see it essentially ensuring that equipment is online. The image capture rate is stable and so forth. A lower section is identifying density of individuals within the environment. And on the right, this are essentially alerts generated, real-time alerts generated that need to be processed by a security team or someone else. So again, this is a good example of a real-time dashboard using the same data processing, same data set as our other uses. Here's a screenshot I took just in case our processes are a little slow and grumpy to get going this morning. But here's another example of using the same data set, but obviously in a completely different manner. This is a historical data set using perhaps millions of records to look at trying to identify a correlation of persons and locations and movements and patterns and related to security incidents. So again, this is taking that same data, perhaps trending or using a much longer historical viewpoint, and perhaps integrating with other data sets, performing some very complex and very computational intensive calculations on this. And so the takeaway would be you can support both workloads in the same system. Traditionally in the past, this may have been more of a batch-driven or ETL process to be able to support the analytics at this scale, but that's not necessary. So it's also a good time to step back and talk about core application requirements. These are feature requirements. It's very specific to what an end user will be using this for, but all applications do have core requirements, and we've compiled a set of core requirements that span many applications, and Sudha has some words of wisdoms to share on this.
So here is a grid of typically core requirements for any modern application, especially the ones that are needed for real-time data processing. In this application as built by Randall, we're going to focus on 4 most important ones. The first one is performance. Near real-time, low latency apps are always good to support as real-time as possible data ingestion, visualization, and alerting. The second one is scalability. Obviously, this system needs to be able to handle anywhere from 0 to hundreds of thousands of images coming in per minute. How scalable is your system to scale up and down as per incoming requirements? How fast can you do that is also very important requirement to take care during your design process. Another one is resilience. You never want your security systems to be down. So how well have you designed the system to support high availability, again, is one of those core requirements of the system. In addition to all of this is dev life. We also care a lot about agility. How fast, if you find a problem, can you fix it, run through the entire pipeline, deploy the changes, and actually see the bug fixes in effect? So agility, building, deployment for systems end to end. Other than that, there are also the other ones, security and compliance, for example, for such an app which is dealing with images, PII data is quite important. We also want to talk about, because we want to scale dynamically, cost optimization, pay only for what you use when you use it. OCI systems allow you to do that very easily. Randall will take it away from here with in-depth, how did this design solve all of these requirements?
Thank you, Sudha. Now, optimal modern designs will apply or favor design principles to deliver on application requirements. I've selected the 7 most relevant principles to focus upon. The others are also important, just not as high of a priority for the requirements we've identified. I like to think of this first group as delivering on performance and availability. With decoupled services, you get modular components that are individually scalable and allow for upgrades to smaller pieces of the environment, so much less risk. And with modern cloud infrastructure, your APIs and service endpoints are more easily made auto-discoverable to minimize complexity. Statelessness in the application tier is important for scalability and resiliency because resource capacity can be increased or decreased transparently, and component recovery can happen gracefully. Now, it can be challenging to implement idempotency in this stateless application tier, meaning an event, a message can be processed and delivered any number of times while the final data set is still accurate. We'll show some best practices on how to handle this. On the infrastructure side, robustness and self-healing should be expected. From a development standpoint, you should take advantage of the underlying infrastructure, automation, and resiliency to implement application robustness with minimal dev effort. So let's see an example of dynamic scalability and transparency. So here's a diagram showing how you should view these principles applied to our stack. So why is this important? Well, in a functional sense, you can scale up resources as required and recover failed components gracefully. And it also opens up options to select the ideal platform for each tier or component. We'll specifically cover options for the backend data storage. Now, this is the front end. You won't always have the ability to update the event data generators directly, or it may be impractical to push an interface schema change. But if you can make some updates, it may be helpful. To be clear, don't add processing overhead or anything to add latency to the front end processing. Just use readily available environment data if possible. Consider how the metadata could help processing efficiency downstream or maintain statelessness in the app tier. And this is the back end. There are several data storage and management options that you should consider improvements to traditional platforms in terms of scalability and license cost reductions or eliminations. Things have changed a lot in the last few years. The demo we saw earlier is actually running on a very small, fully managed MySQL database that scales up to several million records per partition, several hundred million records in the small operational database. Now here's a query supporting our dashboard for the demo. It's for a relational, dimensional, or columnar database. It's a very simple query, but not so much for a time series database or an NFS object storage, file storage, HDFS type storage system. And let's take a look at some of the features that are built in to this type of data platform. We had talked about idempotency. Uniqueness is very easy to implement on the back end. It may be in a staging table, or if it's a small enough number of records, that could be part of the query itself, as it is here. Again, very easy to implement in this type of stateful data store. As far as partitions go, maintaining an ideal optimal processing size of data is important, of course, but that's easy. Most event data is time series or time driven. So having partitions to cover a span of time, whether it's a day, week, month, quarter, is usually very easy to rotate in and out. As far as aggregations go, very simple to do. Of course, this is a very simple aggregation, but think of the complexity you can leverage right in the service itself. As far as data source integration, of course, it makes it easy whether or not it's hosted within this instance or external. And of course, filtering, grouping, everything you've counted on for years now is readily available. So the summary, having a traditional data platform on the back end with modern scalability built into it can help achieve a stateless middle tier. Well, that was the front end and back end. Let's take a look at what we mean by heavy lifting on the application tier itself. These are some of the core functions that the application tier should function, and if possible, in a stateless manner. So the authentication and buffering, we've talked about that. Very likely your API endpoint may have minimal or external authentication on the data. So having the ability to filter and validate incoming data is very important. Can be very process intensive, but easily implemented with scalable functions or other serverless processes. Same goes for data validation, whether it's filtering for an injection attack or any other schema compliance. It can be a process intensive, but very easy to scale up on the middle tier. In this particular example, our demo, it has very significant processing on binary files to extract face landmark vector data. So very processing intensive. Oftentimes the middle tier, application tier, is simply examining data, moving it onto the system, making that available for downstream analytics. But then in this case, very heavy processing, but very easy to scale up using functions. Of course, being able to modify the schema or add annotations is also important. And one more thing on the routing, message routing. What we've seen in the demo is essentially a single lane, a processing of data, a data pipeline, so to speak. But in reality, most event processing systems will examine data and make a determination of whether or not it needs to be sent to a fast track path for perhaps an alert generation process or perhaps archiving data. So this group of design principles I like to think of as agility and portability. Now, definitive, repeatable, audible processes should be part of your change managed process, of course. Nothing new here, except in the cloud, you get a couple of extra bonuses. You can quickly replicate entire environments, for example, to perform a regression test or a root cause analysis test. And the deployment automation can also be integrated into your application for scalability and recovery. Oracle has partnered with HashiCorp to integrate Terraform into the infrastructure. It's portable, but also hosted as an integrated managed service. Unlike some other platforms you may have seen in the past, like CloudFormation or ARM templates, it's not proprietary or tied to a single platform. As far as containers, you probably already know the benefits of containerized applications. Most managed services, managing functions nowadays, are container-based, and the development is becoming very similar, whether it's a traditional container application hosted on a cluster or and a function itself. The Oracle uses the FN framework. It's an open and supported project. It simplifies the process of developing and deploying functions. Now, traditionally, there have been two big challenges for adopting or migrating function development. One would be the secure parameter and data transfer upon the function invocation. And another is visibility into the performance, state, and health of the application runtime, seeing how it is within an additional layer of abstraction. So let's take a look at how we can implement those. Before we do, I just wanted to show this diagram, which is very closely related to most production implementations of the event processing demo that we have running. We don't have to dig into the details, but I just wanted to point out some of the complexity. This is just a high-level diagram showing some of the functional components. Keep in mind that any individual component needs to be redundant, have automatic recovery built in, and think of all the additional layers of management that's built into this. So wanted to show this just to think about traditional ways of development and ensuring you have all of those management and recoverability features built in. It can be very overwhelming and complex. However, implementing the design principles, automation, and serverless platforms we were talking about, this actually is very surprisingly easy to implement. So we were talking about some of the challenges of adopting or migrating to function development. This example is in Python, but of course you can use almost any platform you prefer. When you're running functions within the FN framework, the Managed Function Framework, and Oracle Functions, you actually have the ability to assign very specific and granular permissions to the function runtime. This can be used to integrate with other services. You can leverage these credentials to integrate with your application components and so forth. It makes it very easy to, instead of having to bootstrap calls into a credential vault, for example. That's not always possible though. So if you look at the yellow boxes here, it's showing an easy way that the framework automatically allows you to pass environments or runtime or deployment time credentials into, or any configuration value into the runtime of the function itself. For example, this could be important to pass credentials for the application level. Maybe it's external to the cloud infrastructure environment. So this is a very easy way, built-in way to securely pass in environment variables. And the blue box is also an easy way to manage the transfer of data sets, however large or small. This is a JSON format. It has a very large potential payload of size. And as you can see, it's very easy to manage. Just any application calling the function through the API can pass a JSON package, and all of that data is readily available. We also talked about having visibility into the function runtime itself, and the Oracle Function Framework makes that very, very easy. Again, this is a Python example where you can see just using the native standard logging utilities automatically gives you the ability to generate and pass any information external to the function. Not only that, this information is captured securely and stored within the logging service. So you do not have to manage any sort of external data targets, any information, whether it's monitoring metric, error, or simply a configuration or event, can be easily generated and passed into the logging service with very minimal efforts on the development side. Wanted to also take a quick look at Terraform. We talked about the automation. So Terraform, like many other automated deployment frameworks, is declarative. So here's some code sample of actually capturing the environments, the demo environment we're running. As you can see, it's declarative. You define the services and configurations, and Terraform will apply that. This has been a fantastic benefit to help my development personally, but it's also a learning curve, as you can imagine. Fortunately, Oracle makes that much easier to adopt Terraform and automation. Let me just log in and we'll take a look. So as mentioned, Oracle has integrated Terraform into the infrastructure service. Here's the landing page for Resource Manager, which is the management stack for Terraform. As you can see, you've got a lot of good getting started in tutorials, but also makes it very easy to manage your stacks. So to develop the code and upload a stack, that's one option. But to get started, you can also create a stack from an existing environment as a starting point. You can select your compartment, location, services, all services within the environment, or specific configuration and components, and go ahead. It will automatically generate a stack and generate the code similar to what we just saw. In this particular case, since I already have a stack generated from another region from where we're actually running the demo, we can go load that and deploy this right here in this region. So this stack is been uploaded into the resource management console. And we can go ahead and apply that, and it will build out an identical region or identical environment to our demo in another region, or updated with any configuration changes you may have made. We'll take a quick look. It should be generating some resources. Brand new environment and all the other resources to make an identical demo environment. Fantastic. Let's move on to another set of design principles, and this one I'd like to call focus on your code. Now, regarding managed services, so most people are familiar with the benefits of managed service, namely offloading complex management tasks, but also sometimes the challenges, which can include a possible subset of features or configurations compared to a self-managed option. In my experience, I can say that those advantages almost always far outweigh the challenges. And many services carry no additional usage or license charges on top of the underlying core resources being used. For example, deploying an Oracle Kubernetes engine cluster to run your app. You only pay regular virtual machine rates for the specific worker nodes selected. There's no cost for the redundant API and control plane servers, nor the cluster of management automated services itself. It's a great deal. And of course, with managed services, you have frontline support engineers with developers on standby ready to help resolve any issues you may encounter. Now, monitoring and tracing capabilities are already integrated into the infrastructure and the serverless platforms, and there are also hooks available for your app runtimes to use. You know, we already saw the logging integration in our functions. But there are many other services such as audit tracing, resource monitoring to complete a comprehensive set of capabilities. These services make it fast and easy to implement monitoring features early on in the dev cycle. So wanted to show our demo design we have running in the background, the topology design one more time. Hopefully the reason or the design principles, how they've been applied to this architecture are a little more evident now, and you'll be able to take those for your own designs. And summarize the design principles that were used. Here's some additional resources to help get you started. Now let's get to some questions. First question, what dashboards or analytics tools are available? Well, OCI presents the Oracle Analytics Cloud. This is a full-featured and completely managed cloud service. Has a lot of the features you may be familiar with other Oracle tools. It's a great service for any of your reporting analytics dashboards and so forth. That being said, OCI is very open to supporting third-party and commercial and open source tools. Made a big investment to ensure that you can bring your tool of choice and plug right into the infrastructure, whether it's the data systems or the services that are collecting data for you. In fact, the demo we saw earlier used Grafana for the dashboard, open source Grafana. Next question. Are there situations where a virtual machine would still be preferable over a function for event processing? I get this question a lot, mainly from teams looking to maintain their investments in an application or platform. There are situations where it may be preferable to use a VM instead of a serverless type platform, particularly if the event generator might spawn a bidirectional communication or start a session and so forth. That workload may not align well with a true event-driven processing framework. So that's one example. Another, although it's very rare, but a high security type of application that might have a federated authentication system, might require static IP, other advanced configurations from a long-lived process. That's an example where a serverless, a function type environment may not be the best. But again, that's pretty rare. Good question. Another one, doesn't Oracle Streams have a finite message throughput? How does this service scale? A good question. So Oracle Streams, each partition, in fact, of a stream does have a finite throughput. So the way to scale up a stream would be to add additional partitions. That's very easy and oftentimes completely transparent. There can potentially be a little bit of overhead on your middle tier to coordinate the reading and writing messages from different processes to make sure you're load balancing multiple partitions. But that's straightforward. I found actually one of the more common scalability issues with using streams would be not the amount of messages being written or read from a partition or the amount of data with those finite limits, but the number of API calls. So best practice would be to batch your API calls, batch your messages into less API calls to maintain your throughput or scale up your throughput without hitting the API limit, per second API call limit, which is actually a more common bottleneck we've seen and easy to resolve. Okay, great. Next question. What development platforms are supported with Oracle functions? Well, certainly a Java, Python, Node, Go, Ruby, others are fully supported, and they come with ready-made templates and code samples for you to get started and just drop your own code in. However, you can in fact bring any language or platform as long as it's built and packaged as a container. There are guidelines on how the entry point is configured, the keep alives, and so forth. But it's pretty straightforward, and there's lots of documentation to cover that as well.